Welcome to monochemistry. In this lesson, we're going to learn about Le Chatelier's principle. In this principle, a system at equilibrium that is perturbed, or disturbed, or manipulated, whichever one you like, will shift so that it returns to equilibrium. Basically, any system at equilibrium, if it's manipulated, changed in any way, will always make a shift so that it goes back to equilibrium, whatever it needs to do to go back to equilibrium. Now, this handsome devil right here is Le Chatelier, or as I like to call him, the cat. Get it? Because Le Chat, the cat. Anyway, kind of looks like a cat, right? See the resemblance? Anyway, Le Chatelier's experiments showed that there are several ways to manipulate equilibrium systems, and those include changing the concentration of both the reactants and the product. They include changing the temperature of the system, and they include changing the pressure of a system. In this lesson, we're also going to talk about the effects of inert gases and catalysts on equilibrium systems. So get ready to take some awesome notes, and I expect to see very awesome drawings like mine in your notes. So the first one, if we're going to look at Le Chatelier's principle, is the increasing or decreasing of the concentration of the reactants. We're going to take notes on the reactants, and then I'm going to get you to predict what would happen if I did the opposite and increased or decreased the concentration of the products. Okay, so we're going to look at just the reactants this time. And in order to do this, I've got a little reaction chamber, and that's this guy right here. This is my reaction chamber. And what I'm going to do is I'm going to put a few of these gases. Remember this, and I didn't represent this very well, but this equation, you can write this down. It should be at equilibrium. Okay, so I didn't do a very good job of that. It should be at equilibrium. Let me try that again. There. Should be at equilibrium. Okay, so I'm going to draw a few just really quickly, and I've got my little key over here. Okay, so this is the nitrogen plus hydrogen yields ammonia, and I'm just going to draw a few things here. Going to get my nitrogens. Oh, that doesn't show up very nicely on there. And then I've got to get my hydrogens. Okay, so let's say that this is the initial concentration of the equilibrium system. So right now, this system is at equilibrium. Okay, so draw that. Now what you're going to do is you're going to draw a new equilibrium system with more reactants. Okay, so you're going to draw another picture now showing that we've increased the concentration of the reactants. So I'm going to add more of these. And get my yellow back. More of those. Now, based on collision theory, if I increase the concentration of reactants, what should happen? Well, the reactants should collide more, thus creating more product. So, if I increase the concentration of those two things, now what you're going to do is you're going to draw another picture. I've increased the concentration of these things here. You're going to draw a new reaction chamber and watch what happens. They are going to react. Boop, 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 boop. That's them reacting, by the way. And they are going to form product. Okay, so there's three pictures. One with the initial reaction at equilibrium. We perturbed it. We added more reactant. And what happened? The result was those reactants collided with one another, creating more product. So here's what Le Chatelier's principle says about that. If you increase the concentration of the reactants, the reaction will shift to form more product and reach equilibrium. That's it. Now here's the cool thing. If I was to decrease the concentration of the reactants, the reaction would shift to the reactant side. The products would collide with each other and reform the reactants. It would work in reverse. What do you think would happen if I increased and decreased the concentration of the products? The second one we're going to look at is increasing or decreasing the temperature of the reaction. Now, in order to understand the effects of increasing or decreasing the temperature on the equilibrium system, remember this is a system at equilibrium, we have to look at what is called the delta H. Okay, now the delta H is the change in enthalpy. We looked at this before. A negative delta H indicates that the reaction is exothermic, which means it gives off heat. A positive delta H means that the reaction is in fact endothermic, which means it absorbs heat. If we pretend that the delta H is part of the chemical reaction, then it makes the idea or the concept of Le Chatelier's principle with respect to temperature a little bit easier to understand. So in this case, we're going to add 46 kilojoules per mole to the product side. Why? Because it's releasing that energy. Okay, so in other words, nitrogen plus hydrogen yields ammonia plus energy. Makes sense, right? Okay, remember, temperature is a measure of the average kinetic energy of the particles in a particular area. If I increase the temperature, those particles will have a higher kinetic energy, which means overall they will have more energy. Okay, so if this is a system at equilibrium, if energy plus ammonia gives me products, energy plus ammonia gives me reactants, and reactants plus reactants gives me ammonia and energy, what's going to happen if I increase the temperature? Well, if I increase the temperature of an exothermic reaction, that means there's going to be more heat available. If there's more heat available, it's going to react with the product to form reactants. Okay, so write this down. Increasing the temperature of an exothermic reaction causes more collisions between products, shifting the reaction to the reactants side. Okay, so that's that one. What if instead of increasing the temperature, I decrease the temperature? If I decrease the temperature, that means there's less energy available on this side for the ammonia to react with to form reactants. Therefore, the shift in this case will go, the shift will be that way for that one. The shift in this case will go towards the products. If I remove some of this heat, the reactants will collide more often, forming product. And that will allow more energy to be produced to get back up to normal. Before we get to this one, it's important for you to also write down what you think would happen in an endothermic reaction. In the previous part, I only talked about exothermic. Write down what you think will happen in endothermic. Let's talk about increasing or decreasing the pressure of the system. Remember, this is a system at equilibrium. If I increase the pressure, in essence what I'm doing is I'm decreasing the volume. With less volume, there's less space, which means there's going to be more collisions. In order to figure out what's happening, if I increase the pressure in this particular reaction, I need to look at what I have in here. Now, at equilibrium, I have 2 moles of ammonia gas, I have 3 moles of hydrogen gas, and I have 1 mole of nitrogen gas. So if I decrease the volume or increase the pressure, which ones of these are more likely to collide? Well, they're actually all more likely to collide than they were before because there's less room. But notice that there are 4 moles of gaseous reactant and only 2 moles of gaseous product. So which one is more likely to react with the other? Well, because there's 4 moles of gaseous reactant, they are now more likely to collide than they were before, and they're also more likely to collide than the 2 moles of product. Therefore, if I increase the pressure on a system at equilibrium, the reaction will shift to the side with the fewer number of moles of gas. In this particular case, it's going to shift towards the products. Now, that's not always going to be true. You have to look at the number of moles of gas. It has to be a gas. And that will determine which way the reaction is going to proceed. In this case, it would be towards the products. Now, for another particular instance here, if we decrease the pressure, that means if we increase the volume, the opposite is going to be true. It always shifts to the sides with the fewer number of moles. So if I decrease the pressure, it shifts to the side with the fewer number of moles, which in this case is going to be with the greater number of moles, Mr. Monahan. If I decrease the pressure, it shifts to the side with the greater number of moles of gas, and that in this case would be the reactant side. If I were to add a catalyst or an inert gas to this reaction, let me just put a few things in here. Great drawings, I find. Okay, so there's my drawings. If I was to add something else to this, whether it be a catalyst or some other gas, inert means that it's not reactive, so it's not going to react with the stuff that's in there. It's not going to change the rate of the overall reaction at all. It's not going to shift the reaction towards one side or the other. Now, catalysts, what do? They speed up the rate of chemical reactions. But in an equilibrium system, catalysts increase the rate of both the forward and the reverse reaction. Therefore, since they increase those both equally, a catalyst has no effect on the equilibrium system, and there is no change to the equilibrium position of the system. Likewise, if I add an inert gas, since it's not reacting with anything, it doesn't really take up any more space in there compared to the other molecules that are there. It has no effect on the equilibrium position of a system. All right, folks, that in a nutshell is Le Chatelier's principle and how different aspects of manipulating a system at equilibrium can affect the equilibrium and cause it to make a shift in a particular direction. Bring your questions to class.